Hey guys, Miss Peterson here, and today we're going to be using the optics bench to learn about diffraction and interference. We're going to be doing a series of 3 short little demonstration-like experiments. First, we're going to use this diffraction grating to find the wavelength of an unknown light. Okay, I have a green and a red laser pointer here. Then we're going to use that now known wavelength to find the diffraction spacing on these diffraction glasses. You guys might have seen these before. If I turn these toward you and put them on the camera, we should be able to get some cool effects, okay? Different wavelengths of light diffract differently, so that's how these work, to separate light, such as this white light, into all of its colors. And then, last but not least, we're also going to be using this same setup to find the thickness of a piece of my hair. Okay, cool? Okay, cool. Let's get started. Okay, so before we get into all of the problems that we're going to do, I want to go over the equation that we use and define all of the variables. So in our diffraction pattern, okay, we have D, which is the distance between the slits. We have L, which is our distance between the screen and the slits. We have our maxima, that is what the M is for. And then X, okay, is going to be this distance between the maxima. Between maxima. Now, the version of this equation that's on your equation sheet is d sine of theta equals m over L. Okay, remembering that sine is going to be x over, I'm going to call this one little l for a second. Okay, so basically this says for whatever maxima, it's going to be some multiple of the wavelength, because the difference in those paths is going to be what, if it's equal to one whole wavelength, then you get that first maxima. Okay. However, we more often use this form of that equation. So I'm going to show you where that comes from. It's called the small angle approximation. So for small angles, okay, we can say that L is approximately equal to L. Okay, little l equal to big L. The difference between these two paths is going to be really, really small compared to their size. It'll be on the order of a couple of wavelengths of light, so nanometer order, when this spacing is normally on about meters, the order of meters. So that is also why, though, this gets less accurate the further out you go from the maxima. This equation does get less accurate. But for small angles, for those first maxima, sine of theta, which is x over little l, is approximately equal to tangent of theta, which is x over l. So if we put that formula into here, okay, times x over l, times the wavelength, and we do some reorganizing, okay, we end up with the equation you see here that we're going to be using for all of our experiments. Okay, cool? Okay, cool. Okay, so experiment number 1. We have this diffraction grating here, okay? It has a spacing of 5,276 lines per centimeter. So we can use that number to figure out the spacing between each individual line. I'm going to place it right here at the 300 millimeter mark. Okay, our diffraction scale is back here at the 100 millimeter mark. So the distance between the diffraction grating and the screen is 200 millimeters. Now, I want to show you a couple things before we get started. First off, with the laser light. Whether I have it back here, go ahead and watch the scale. Okay, as I move it closer to the diffraction grating, note that the position of the interference pattern doesn't change. Okay, that variable doesn't affect the interference pattern. It's only the distance between the diffraction grating and the scale. If I change that one, okay, go ahead and again, watch the diffraction grating. I can get the dots to move closer together as the screen gets closer to the scale, or I can get them to move farther apart as the screen gets farther away from the scale. Okay, so let me put it back on that 300 millimeter mark, and let's go ahead and make some observations. Okay, we'll start with the green light because it's a little easier to see. So if I shine that green light, I'm putting the brightest maxima, the m equals 0, right at that 0 point. And then you guys should be able to see the other two. It looks like they're at right about 6 centimeters away from that brightest maxima. Maybe a little over, maybe closer to 6.1, but I would say 6.05 or 6.1. Now, note the red one, okay? Let me get this red one going. This one's a little dimmer. It might be harder to see. Let me go ahead and turn off the lights so that we can see that better. Okay, that should make our data collection a little easier. Let me go ahead and get that red light there. And there we go. We see with the longer wavelength, we have an interference pattern that's a lot more spread out than it was with the green. The green is still right around 6, and the red looks like it's closer to about 7.5. Okay, I would say right around 7.5 centimeters between the m equals 0 and m equals 1 maxima. Okay, so 7.5 centimeters for the red, and looks like about 6.0 for the green. Okay, cool. Okay, cool. Okay, so to find the wavelength of the laser light using the known diffraction grating, first we need to figure out what the spacing between that diffraction is. Okay, basically how many space there is between the lines. On most diffraction grating, they give you the spacing, for example, how many lines there are per centimeter, and then we have to convert it to figure out the spacing between the actual slits. So in order to do that, we just kind of have to flip the number. So if there is 5,276 lines per 1 centimeter, if we divide 1 centimeter by the number of lines, that'll give us the space of each individual line. Now, I'm going to do one other step in this calculation, which is to convert it to meters. I just want to have the same units throughout, and we think meters is going to be the easiest way for us to do that. So I also know that there are 100 centimeters in 1 meter. Okay, so I can plug that into my calculator. 5276 divided by 100 in scientific notation, and we get a spacing of 1.895 times 10 to the negative 6 meters. Okay, so that's how much space there is between each individual line. So then the distance L from the screen to our slit is 200 millimeters, which is equal to 0.02. Hold on, I can math. That means if there's 200 millimeters, there's 1,000 millimeters in 1 meter, aka there's 0.20 meters in between the diffraction scale and the slits. Now, for the distance between the maxima, we are looking here at our, okay, I'll label it, this right here is our m equals 1 maxima. Okay, the 0 is on the 0 mark. Now, it was a little hard to tell in the video, so I posted some stills from the video up here for you guys to see. And if we zoom in on that, okay, we can see, I know I said in the video it was 6 or 6.1. If we're looking here, it's looking like it's closer to 5.9 than to 6. Okay, So we're going to go ahead and go with that number. Okay, 5.9 centimeters. Okay, and then that is equal to 0.059 meters. Now for the red, okay, let's go ahead and zoom in on that. That one, I think I said in the video, is about 7.5, and it does indeed look like it's right around 7.5. So we will just go with that. 7.5 centimeters, aka 0.075 meters. Okay, now it is time to do the calculation. Okay, we are working off of the equation x equals m wavelength L over D. Okay, and we are trying to solve here for the wavelength. So we need to manipulate that equation. Also, we can remember that m is 1, so we can ignore that variable in our equation. So when we do our rearranging, the wavelength times the whole thing by d, okay, so then we have x d, and then divide it by L. So we have x times d over L. Remembering that x is the distance between maxima, d is the diffraction spacing, and L is the distance between the spacing and pattern. In this case, our diffraction scale. So lots of distances there, lots of numbers that have the same exact units, so it's really important to keep track of your variables here. But let's go ahead and solve it out. I have red and then green here, so we will just do it that way. Okay, so first for our red, I'll solve it out in red. Okay. The wavelength of the red light, again, we're using this equation, will be the distance between the maxima, 0.075 meters, times the diffraction spacing, 1.895 times 10 to the negative 6 meters, divided by L, the distance between the spacing and pattern, 0.20 meters. So we plug that into our calculator. Times 10 to the negative 6 divided by 0.2, and I got 7.11, okay, times 10 to the negative 7 meters. Okay, often when we're talking about the wavelengths of light, we'll report that in nanometers, so I'm going to go ahead and convert that. We know that 1 meter is 10 to the 9th nanometers. So this ends up being 711 nanometers. Okay, that is for our red light. Now for our green light, it is the same equation, but with different spacing. 0.059 meters times 1.895 times 10 to the negative 6 meters divided by 0.20 meters. And we get okay, 5.59 times 10 to the negative 7, which will be 559 nanometers. Okay, so we did get that red has a longer wavelength than green. That is a thing we know, so that's good. Now, on the actual laser pointer, they report the wavelengths of the light. They report them with a certainty of plus or minus 5 nanometers. Okay, so granted, our red is a little off. Our green is less off, but you know, it is what it is. So we can actually calculate our percent error if we needed to. Our percent error from the red Remember, for percent error, it's always going to be the difference between the values. Hold on, let me get a better. Divided by the theoretical. And then you times it by 100 to get it in percent form. So for red, if we were calculating our percent error, it would be 711 minus the actual wavelength, 750, divided by 650. Did I say 750? I meant 650. Okay, and then we times it by 100 to get it in percent form. 711 minus 650 divided by 650. Kind of a high percent error. We have a 9% error on that one. Not my best. It is what it is. For the green, we should have a much lower percent error. That one looks a lot more accurate. Oops, I don't know why I did that way. So we only got a 5% error on that one. Not bad. I'll take it. Okay, cool? Okay, cool. Okay, so now let's find the diffraction pattern for the optics glasses. Okay. No, we still see this one has diffraction gratings going vertically and horizontally. That's why we get that kind of diffraction. Okay, and you can see that these ones are a lot closer together. It still follows the trend. This green looks here, it's like it's at about 2.2, 2.1. And the red, since it's a longer wavelength, should be a little bit more spread out. And indeed it is. It looks like it's at about 2.6. Okay, probably 2.6, maybe 2.7, but right around there. So again, the green is at about 2, maybe 2.1, and the red is at about 2.6. Okay, so now we're going to use that known wavelength of light to find the diffraction grating or the diffraction spacing of these CPO light and optics diffraction glasses. So some of our setup is the same. We still have the same distance between the diffraction grating and the diffraction pattern or the diffraction scale. We now know the wavelengths of light. I'm using our known wavelengths, not our ones that we calculate. And we need to figure out our diffraction grating spacing. So if we are looking, I think in the video I said it was at about 2.0, 2.1. And if we zoom in and look here, it looks to me like it's a little bit past 2. Okay, the center maxima looks a little bit off from 0. And if you're looking at this spacing versus this one, that one actually seems to be a little bit past 2. So I'm going to go ahead and go with 2.1. Super precise here. So it's at about 2.1 centimeters away, which is 0.021 meters. Okay. So now for the red one, let's go ahead and get our variables. In the video, I said it was at about 2.6, and indeed, if we zoom in here, okay, we have a little bit of disagreement because the maxima on the left looks closer to 3, but this one looks closer to 2.5 because I didn't have the glasses perfectly flat. You can see it's a little bit at an angle there. So let's go ahead and go in the middle of those and go with, what do you say, 2.6, 2.7? Let's go with 2.7. Again, we're looking to get on the right order of magnitude. This is not a very precise experiment by any means, but hopefully we can get some agreement between the diffraction spacing that we get from using the green laser to the diffraction grating we get from using the red laser. So we're working off the same equation, but now we need to reorganize it to solve for D, the diffraction gradient spacing. So when we do that, we move it over, divide by X, and we end up with D equals M wavelength L over X, okay? But now remember, M is 1, so we can pretty much ignore that one, okay? Camera keeps moving on me. So let's go ahead and plug it in. I'm first going to do it using the green laser. Come on, there we go. So our diffraction, based on the evidence collected using the green laser pointer, is D equals the wavelength of the green light, 532 times 10 to the negative 9th meters, or 5.32 times 10 to the negative 7 meters if you're doing correct scientific notation. I'm just using the nano as 9 because that's easier. 0.20 meters for the spacing between the diffraction grating and the screen, okay? And then X is the distance between those maxima, so 0.021 meters, okay? And I plug that into my calculator, and I get 5.06666, so 5.07 times 10 to the negative 6 meters. Okay, not bad. Let's go ahead and see what we get using the data from the red laser pointer. So D for the red, same equation, but with the wavelength of the red light and the spacing of the maxima on the red light. Oop. Divided by 0.027 meters. Okay, and we plug that into our calculator. To the negative 9th times 0.2 divided by 0.027, and we get 4.81 times 10 to the negative 6 meters. Okay, so they're both at right around 5 times 10 to the negative 6 meters. Okay, a little bit off, but not too bad. Now, if we wanted to then take that spacing and use it to find out how many lines per millimeter we have, we can do that. So that is the spacing between the lines, and we want to get it to lines per millimeter. So first, we need to kind of take the inverse of this number. So we know that for every one, let me see, where is it here? For every 1 meter, for every 1 space, I guess, but we'll go 1 line, there is a space between it of 5.07 times 10 to the negative 6 meters. Okay, so 1 line and then a space of that many meters. So if we want to get to that 2 lines per millimeter, all we needed to do is convert our meters to millimeters. So we know in 1 meter, there is 1,000 millimeters, or 1 times 10 to the 10 to the 3rd. Well, okay, so we can go ahead and calculate this out. Divided by 1,000, and we get that there are 197 lines per millimeter. Okay, using the other equation, we get that there are times 10 to the negative 6 divided by 1,000. We get that there are 208 lines per millimeter. So there's probably about 200 lines per millimeter on our CPO glasses, which makes sense. We know the diffraction grating was or spacing was much closer together. So that means we have more spread out slits. For our other one, it was about, let's see, where did we get that? The spacing was at 527.6 lines per centimeter, or a spacing of 1.8 times 10 to the negative 6. So our spacing is on the same order of magnitude, which is good. That means they will both diffract light, which we did see in both experiments. So yeah, we're looking good there. Okay, cool. Okay, cool. Okay, and now last but not least, we're gonna try to find the thickness of a sheet of hair by using the two sides of the hair like a double slit. I'm gonna stick to the red light since the red light tends to be more spread out. Okay, there you can almost see, let me see if it's easier to see with the green light. Okay, if I get it shined right on the hair, you can almost see the diffraction pattern. But you'll note that when it gets there, the maxima are super close together. Okay, they're not really able to be distinguished. So we can fix that by giving it more time to travel. I'm gonna move this all the way back to the 600 millimeter mark. Okay, let me scoot that so you guys can see. 600 millimeter mark. And now I want you guys to pay close attention to that. Start with the green light. There we go. We can see that diffraction pattern showing up, but let me see if I can get it situated where it's supposed to be. So we can actually get a number reading here.
Move it on up. Too high up. Come on, let's get it somewhere where we can get a measurement. There we go. Okay, well, the brightest maxima is at 1. But I think that should be good enough for us to get a measurement and kind of see its effects.
I'll go ahead and zoom in and post a picture of what it looks like zoomed in. Okay, so here's a zoomed in still of that diffraction pattern. Note, this diffraction pattern is way closer together than the diffraction patterns we were seeing in the other two experiments. And that makes sense. I can see a strand of my hair, okay? My eyes can determine that. On the diffraction grating or the diffraction spacings, we couldn't even see the slits, the spacing between the slits. So that makes sense. This is obviously going to be a much closer together diffraction pattern because we have a much bigger difference in the slit spacing. Now, this is so different that I don't even think I'm going to be able to use the m equals 1 maxima. Okay, if you see there, there's our m equals 0, and it actually looks like it's at about 0.1 centimeters. Okay, let's keep that in mind. Now, there is probably our m equals 1. There's our 2, and there's our 3. Okay, I'm going to go ahead and use the m equals 3 maxima. I can see that one pretty clearly, and it's just going to make our lives easier. Okay, so if I zoom in, that m equals 3 maxima looks like it's at about, okay, 1.1 centimeters. Okay, so that gives a spacing between our m equals 0 and m equals 3 at about 1 centimeter. Okay, and that'll make our calculations pretty easy too. Okay, so we have our distance L has changed. I said that I put the hair on the 600 millimeter mark. And this, if you remember, was on the 100 millimeter mark. So our L is 500 millimeters or 0.5 meters. Okay, we're using our m equals 3 maxima. I was only able to get a good still on the green light, so we'll use the wavelength of the green light, which was 532 times 10 to the negative 9th meters. And then we need our x, our distance between those maxima. So we said that was 1 centimeter, which is 0.01 meters. Okay, So we're using the same equation that we've been using, okay, which is x equals m wavelength L over d. Okay, this time we are again solving for the distance between the spacing, that d. So it is d equals m wavelength L over x. And we can go ahead and plug in our values and then see if our answer is reasonable. So our m is our third maxima, wavelength 532 times 10 to the negative 9 meters times L, which was up to 0.5 meters, divided by the distance between that spacing, 0.01 meters. Okay, and we plug that into our calculator. 3 times 532 times 10 to the negative 9 times 0.5 divided by 0.01, and we get 7.98 times 10 to the negative 5 meters. Okay, so of course I want to know, is that reasonable for the thickness of hair? So we went ahead and we Googled it, okay? And it says hair 0.04 to 0.06 millimeters thin, okay? So let's go ahead and convert this to millimeters real quick. We know in 1 meter there are 10 to the third millimeters, okay? So when you do that, you get 0.079. So 0.08 millimeters. Okay, so that is average. Okay, hair with a diameter of 0.06 to 0.08 millimeters is average. Average on the thicker side. Cool. Okay, so that is what we have. We have found the wavelength of a laser light using a known diffraction grating, then used that known wavelength of light to find the diffraction grating of a thing. And we have also found the thickness of a piece of hair using its diffraction pattern. Okay, cool? Okay, cool.